Okay. Yeah, so assignments I handed back, there were like recent things, and I'm trying to clean out all the paperwork in my office. Those of you who've been in there know that there's way too much. So I still have a number of assignments, again, some new and old. So anything that I get by today, any of our homework, I'll make sure to have back with me on Monday. So you have as much as possible to go on before the test. Okay, so everything has been covered for test 2. So what I'm going to do is take this time to actually, I was going to say provide a recap of all the material to help you guys get ready for the test, but really I want as much as possible you guys to provide that recap. Any pieces that you can contribute will of course help your classmates. I should mention for any discussion that happens today or Monday, if you guys decide to clam up, I will start calling out people. I know all your names, so don't try that. Okay, so to start things off, so who can tell me this whole chapter? So everything that's happened since the first test. The general problem that everything we've seen has been about solving.
Non-homogeneous equations.
What?
Would be non-homogeneous equations.
That's a big chunk of it, but let's get more specific. What is the in general, like we don't know coefficients or anything, but what is the form of the equation that we're looking at?
You like rod double prime?
Yes.
Oh.
Continue.
Second order. Second order ODE.
Plus
Yeah, it is second order.
QY prime
Yes.
Plus QY.
PHC, Q2.
Yeah, and we've spent some time on the case where P and Q are constant. For a time being, we're going to let these be general. That's why I left space in here. So both cases are of interest. And then equals what?
You said white prime.
Yeah, I always forget that. Okay, so, thank you. Equal. Well, yeah. So most general form is this one. Okay. Now, this problem, as written, does not have a unique solution. So, what do we need to add to it? Yes, initial conditions. What might the initial conditions look like?
Y
Y0 is equal to 1. Y prime of 0 is equal to T naught.
Yeah, I'll fill in T naught here. Again, in the interest of being most general, is what we have here. Okay, and now this is the DE, the differential equation, and someone said that these are called the initial conditions. So all of this put together is called a what? Well, only the DE itself is second order, but I mean everything. This together with initial conditions, what kind of problem do we call that? It is initial value problem, yes. IVP, okay. And I'm focusing on this because what students seem to have a lot of difficulty with is simply the terms that are being used, the language that's being used. I think any faculty members, department, including myself, would think, wow, we're all speaking a different language, and I bet you guys feel that way too. So I want to put that terminology front and center. Okay, now, so that was the starting point. Now, when we started looking at this problem, so second order for the very first time, we actually got a little bit more specific than this. What watered down version of this did we look at first? Y double prime plus what?
E plus QY.
Yeah. So what do we assume about P and Q? Yes, they're constants. Okay. And we made that 0. So okay. All right, and then we still have initial conditions. So this is all right. Now DE, the second order. Can you tell me what other adjective? Unpack your adjectives. So I don't know if you guys ever watched Schoolhouse Rock, like my generation did, but so your mathematical adjectives. What other term can be applied to this equation?
Non-homogeneous.
It is not homogeneous, and someone else said
Linear.
linear. Yeah. All right. Now, so here it's still second order linear. Now it is homogeneous because of the zero here. And then we say that this is a problem of constant coefficients. Okay. Yeah, the idea is by the end of this class you understand a little more of my babbling than before. Okay. Now, what approach do we take to solve it?
Characteristic equation.
Yes, characteristic equation. Now, to set the stage for, because after this test is over, we're actually going to continue with these kinds of problems. We just go to higher order. So I know that most, if not all of you, could rattle off what the characteristic equation is. But I don't want you to do that. What I want you to do instead is tell me from this, how do I get the characteristic equation? How does it come from this? I actually wrote this in a reading question some assignments back. So I know somebody knows. So like in words, how do I get the characteristic equation from the differential equation?
You said y equal to e to the RC and t take
Correct, although not exactly what I was looking for. But yeah, that is how it pops out. But okay, someone else want to throw something out there?
By changing the order of the derivative to the power of the...
Yes, which is the effect of the substitution that you make. All right, yeah. So order of differentiation becomes powers of r. Okay, and then you guys have rattled this off so many times that you get. I trust you know what that is. You've used it enough times in homework problems. Okay, so now we go ahead and solve that, and you get the roots, which I'll refer to as R1 and R2. Okay, now, once I have the roots, and I'm not making right now, I'm not making any assumptions about the roots. I have two roots as a quadratic equation. What do I do now? Yes, the general solution. Okay, now, without talking about what kind of roots we have, we'll get to that in a minute. Can anyone tell me what is the form of a general solution? And this is true not just of this constant coefficient problem, but any second order linear problem of this form. C1.
E to the R1 t.
We don't know about that yet. We're being more general than that.
y1 of t.
Y1 of t. And then
Plus
yeah, C2, Y2 of t. Okay, so in all these cases we have two solutions. Y1 and Y2 together, what do we call that group of solutions? It's a fundamental set of solutions. So for a second order equation, you need two fundamental solutions to make a fundamental set. If it was like fifth order, you need five of them, and so on. Okay. All right. And so the thing is, if we have two solutions, then we can multiply them by whatever constants, add them together. That is the principle of what? Superposition. With my ears, what I hear is like, yeah. Okay, superposition makes that possible. Only for linear equations, doesn't work for nonlinear. Okay, now let's get to what you guys will be chopping in a bit about. So given the two roots, R1, R2, what are y1 and y2?
Would this be the e to the r1t
When?
when they're real?
Indistinct.
And distinct.
And
Yeah. So possibility number one, the roots are real and distinct. So yes, we have y1 is e to the r1t, y2 is e to the r2t. Okay, so that covers that case. What other cases do we have?
real, not distinct.
And someone else said complex, and we'll cover both of those. So real, not distinct, or also known as repeated roots. Okay, so you're still going to have this solution. Let's call it R1, of a one and only root. And this time, the other one is T. Yeah. Okay, so that handles that case. And then, what was the last case? Complex roots. Where you have a imaginary part. Now, complete the root for me. The two roots are complex. Alpha I'll use as a real part. What else do we have?
Cosine.
Yeah, plus or minus. You're getting ahead of me.
Sorry.
Okay, that's okay. Now, I'll turn you loose. Go.
So you go to alpha cosine beta.
R alpha.
E to the r.
Alpha.
Alpha, yeah, the real part. Whatever's the real part goes in the exponential, and then beta is the imaginary part. Okay, so e to the alpha t times what? Sine beta t, and then what's y2?
E alpha t.
Cosine. Okay. All right, so real part in the exponential, just like up here. That part is always the same, no matter what kind of root you have. And then, since you have an imaginary part now, it goes into sine or a cosine. Now, this was a reading question some time ago. In the case where the roots are distinct, real or complex, you could have these, but in that case you get imaginary numbers. We don't want that, so we rearrange or linearly combine these solutions to get these two. What famous formula makes that possible? Euler's formula. Thank you for pronouncing Euler's name correctly. I recently saw a Facebook post from one of my graduate students about making fun of TV shows and how we pronounce everything wrong. It's like, yeah, I've ranted about that. Okay. All right, so those, and that exhausts all the possibilities. The roots are either real or complex. If they're real, they're either distinct or not distinct. Okay, so now we have the general solution. So, and these several problems on this test will be just like that. I'll say, here's this second order DE with constant coefficients. Write down the general solution, and at that point, you're done. Hold on, my thermostat is acting up again. Oh, that's what I can't help but wonder if that thermostat is trying to drive us all crazy with that long-running, high-pitched whine. Like, this is a building where mathematics is taught. No, it doesn't. No, we already have a way to drive people insane. Okay. All right, so any questions about general solution?
No, but do we have to do that, whatever formula?
No, I just see anybody do it. But practice test tells you what sorts of things you need to be able to do. Okay, all right, that's general solution. Now, suppose I provide initial conditions. So how do you get C1 and C2?
Use the initial conditions.
Yes. Now, more specifically.
Solve two simultaneous equations.
Right, and how do we get those simultaneous equations? And so I'll write down the general form of initial conditions. I had it on the previous board, but I erased it. Okay. So now if you have, I'll box them up. So you have that, and you have this. So we don't really care about these specific cases right now. You only have some general solution that has that form. So the equations to solve.
Is it C1 plus C2 equals 0?
Only if the initial time is 0. So work with this. Look what I have written here and here. Just those two things. Forget everything else. So try and get us to what. So that's too specific. What should the equation be? To make sure that these two are satisfied.
Take the derivative of the one you circled, the y of t, so you can get y prime of t as well.
Yeah, you need a derivative. So, all right. So assume at this point you've done that. So you now have y1 prime and y2 prime. Okay. Then what?
Then you would substitute the values and solve for C1.
Yeah.
and
Well,
C2.
what exactly are we substituting?
T naught for
T naught for t. So we have C1 y1 of t naught. Continue it.
C2, Y2, T naught.
2 of t naught. All right. Equals
Why not?
y naught. Okay, that's your first equation. And then what's the other one?
C1 y prime, y1
y1 prime. Yep.
t naught. C2 y2 prime t naught
Yeah.
is equal to z naught.
Equal to z naught. Okay, so your two unknowns will be C1 and C2. These will be numbers once you plug in T naught, and then you go ahead and solve from there. Okay, that's using elimination and substitution. All right, and then you have your solution to that initial value problem. Okay. So any questions? This really covers actually up to section.
So we have to find the derivatives of those?
Of these, yes.
Okay.
Which, unfortunately, in several cases, is going to require what? Product rule. Yeah, that's needed here, and also here. Okay. All right. So this covers almost everything from sections 3.1 up to 3.4. At least that'll be in the test. Like I'm not going to put a problem in the test. Like computer wants to get into this. So boring.
That would be so easy.
Okay. What?
You can put Ronskins up everywhere.
I can give a really hard Ronskin.
I'd rather you didn't.
What?
I'd rather you didn't.
I thought your math was. All right. Okay. Now, there's one other thing from this earlier part of the chapter. How we determined that this was the second solution for a repeated root case came about by using a technique called Reduction of order. What's being reduced to what by reduction of order?
Second order to
Second
first.
order is
Yeah.
being reduced to first order.
Yeah. So what happens is in that case you're given y1 for that problem, and then by assuming a form for y2 in terms of y1, you get a first order ODE. So in that case, like if I give you a problem that does not have constant coefficients, it's variable coefficients, but I provide y1, then you can still get y2. Okay. Now, actually, reduction of order is a bit of a distraction right now, so I'm not going to say anything more about that. We may come back to it later. Now, once this was mastered, now you'd be able to solve all second order linear constant coefficient problems that are also what? So, second order linear constant coefficient, but this only helps us with
Homogeneous.
homogeneous. Yeah, so only for a case where the right-hand side is 0 does all this work. Okay, now let's talk about when it's not. All right. Okay. So if I return to the most general form of a problem that we had before, remember to prime. Okay. Now the general solution has a different form. We still have the general solution that I wrote before. But what else is needed? What do we call that? What? Particular solution, yes. So y for p of t. Okay. All right. Now, how can we get it? What methods are there?
Reduction of order, right?
No, already talked about that. That's for a different purpose.
What was the first one?
What methods have we covered for getting the particular solution?
You find it like this you find it like this homogeneous and then do something else.
You
Um,
solve them separately.
I'm sorry, I couldn't hear what you were saying earlier.
I don't know.
Okay, all right. Okay, what was?
Do you solve them separately?
Well, I mean, these are handled separately, yes, but as far as just how we get this, there are two methods that I covered.
Method of
Undetermined coefficients. Okay. Undetermined coefficients. What's the other one?
variation.
Variation of parameters. Okay. Now, undetermined coefficients, though, that has some limitations. Variation of parameters can be used for this kind of problem no matter what, but undetermined coefficients can't. What's yeah? So P and Q must be constant. What else? There's one more. Okay. All right. So At least my notes are being looked at. Yeah, G has to be of certain form. Like for instance, the polynomial times an exponential times a sine or a cosine. Things like that, where the form of yp can be determined. Okay, so if that is not true, then what about as a sort of variation parameters? Like I said, it can also be used. So the variation parameters, we assume a particular solution has it's not quite this form. This wouldn't work exactly. But what do we change it to? Yes, it better be in your notes somewhere.
You have to do the varying parameters.
Right. And so what are the parameters that are varying? Like, what? Yeah. So they take the role of C1 and C2. C1 and C2 are constants. Now we let those be variable. So W1 Y1 plus W2 T Y2 T. Okay. But how do we get W1 and W2?
W1 is the integral of GT.
Yeah, we have integral formulas. So integral of
Negative G.
minus G
Y2.
Y2 divided by Wronskian, which is itself a function of t. Okay, and then how's the formula for W2 differ?
It's not negative.
Yep.
Negative and it's y1.
Y1 instead of Y2. Yeah, so whichever one you want, the Y you use in the numerator is the opposite, and then negative sign here, no negative sign here.
That says G what?
G of t.
No, G, does it say right form?
Oh, G has to be of the right form, yeah. Okay.
What do you mean by right form?
That's what I mentioned earlier, but well, the right forms are given in the notes of a text, but for instance, polynomial times an exponential, or polynomial times polynomial times any of these kind of solutions that you have here. Exponential times a sine or a cosine, or just a polynomial by itself. So I wouldn't say arbitrary combinations of those functions, but basically, yeah. Okay, so variation parameters, you can always jump to that. I don't specify on the test, like if I give you a non-homogeneous problem, I don't say, use variation parameters or use undetermined coefficients. Depending on the problem, you might find that you have no choice but to do this. But if the coefficients are constant, if G is of the right form, then you can choose. So technically you get away with not using undetermined coefficients at all. But that's your call. Because once you do this, it's a matter of, once you form the integral, is it something that you can do? Yes?
On the test, are you going to say which method we have to use?
Oh, no. That's the point I was just making, that I'm not going to dictate which method. Actually, there's one thing, not about non-homogeneous equations, anyway. And then for homogeneous equations, the only time I specify a method is reduction of order. But in that situation, you wouldn't have any other option anyway.
So y of p is found the same way for both methods?
Yeah, in other words, you can always do this.
Okay.
Yeah. So for this limited scenario, this is an alternative.
Okay.
Yeah. Because in that case, you have some idea of what the particular solution looks like, based on what G is. Now, no matter which method you're using, if G of t is the sum of multiple terms, you can treat them separately. So figure out a particular solution for the first term of G and then separately for a second term of G, and then just add those together. Although I guess on a test it'd be kind of dastardly of me to do that, but okay. But just saying. Well, I mean, that'd be relevant for the homework on this too. Okay. All right. Now, I covered a good bit of territory in the chapter, but not everything.
So when we find y, p of t, we just plug it back into the general
Yeah.
solution?
Yeah, so you just add it to your homogeneous solution.
And you find that separately, like you take off the y, p of t and find that separately, right?
Yeah, and then just put it back in here. Once you've done that, after you obtain the complete general solution, in other words, all of this homogeneous solution. Yes.
Oh, sorry. I was listening to. I'm really on the method of undetermined coefficients. I'm really confused on how you find the form of y naught t.
Okay, I'm going to come to that momentarily. But yes, that is kind of a pain. After you find the whole general solution, so homogeneous part and particular part, then if you are given initial conditions, you enforce them. It has to be the very last thing. And the reason I say that is because let's suppose you've done this and then you haven't done this yet. If you find a C1 and C2 now, they'll be wrong. It has to take a particular solution into account. So if you give initial conditions, that's dead last step. Okay. Now, yes, undetermined coefficients in finding the form of yp of t. Okay. I'm going to break this. Okay, so finding, and you're asking about the form specifically.
With the a and the a naught.
Yeah, like which terms you need and so forth. Okay. So finding the form of ypt in undetermined coefficients. Okay. All right, I'm going to break this down into a few cases, but I'm hoping that by the time I get to the end of them, you kind of see how the cases are similar. So, if g of t has this form, so the first form we'll look at is some polynomial. So no exponential, no sines or cosines. It's just a polynomial. And the subscript n indicates the degree. Okay. All right. And like I said, you could treat each term separately, but or all at once. That's up to you. Okay. Now, most of the time, if g is some given polynomial of degree n, your particular solution, and I'm deliberately leaving some space here, your particular solution will also be a polynomial of degree n. So a0 plus a1t, a2t squared plus and t to the n. I think the textbook might have numbered the coefficients a little differently, but because they're just being annoying. But the point is, if g is a polynomial of degree n, your particular solution is also polynomial of degree n. You just don't know what the coefficients are. You have to let them be variable. Good so far? Okay. With one exception, and that is, I need to multiply this by some extra factor t to the s for a given power s. And s is how many times 0 is a root of the characteristic equation. I approached this in a somewhat different way before when I was saying, okay, you compute the roots of your characteristic equation because you need them anyway. And you also see what roots would lead to a solution like this. Well, that would be 0. So if there's any overlap between them, you have to account for that by multiplying by the appropriate power of t. But here's another way to look at it is, you have some polynomial degree n, and then if 0 is a root of a characteristic equation, then you have to account for that by multiplying by t or t squared, which t squared would only happen if 0 is the only root of a characteristic equation. So g is a polynomial, take a solution to polynomial. Questions so far? Okay. Like I said, the other scenarios are going to be somewhat similar to this. So I think if you recognize what they have in common, that will help you be able to apply any of them. So the next case is we still have a polynomial, and then we have some exponential, so e to the at.
To the what t?
A. A is a constant. Okay. Well, it turns out this situation is exactly the same, almost exactly the same as the other. And that's, you're still going to have this optional factor, I wouldn't say optional, but possible factor of t to a power if there's a conflict of some kind. You still have a polynomial of degree n following it. But now because you have an exponential in your g, you're also going to have an same exponential, e to the at again, in your particular solution, and the meaning of s is different. S is the number of times a is a root. Again, you're looking for overlap between the kind of roots that would lead to your g and the kind of roots and the roots that you have in your homogeneous equation. However many times those overlap, that's how many factors of t you need out front. And then the last scenario is when you have polynomial degree n, exponential, and I'm writing here e to the alpha t this time, times a cosine beta t, or a sine, e to the alpha t sine beta t. So either one of these, the same form is going to apply, where you're going to have this out front, and then you have, now the work unfortunately doubles, because you have some polynomial of degree n, like the degree you have there, times the cosine one, e to the alpha t cosine beta t, and then you repeat that, different coefficients, for another polynomial degree n, with a sine. Where the power of t out front, s, is the number of times alpha plus I beta. How many times this complex root appears among your roots of your characteristic equation? So, okay, 2 minutes. So first thing you do, look at your g of t, figure out which basket you're in. Is there a cosine or sine? You're doing this. Is there not, but there's an exponential? You're doing this. Is there just a polynomial? You're doing this. And that indicates which roots do you have to pay attention to. You know, is it a complex root in this case? Is it a real non-zero root in this case? Or 0 in this case? So whatever polynomial you'll have in your g, if there is one, you're always going to have that here. So for instance, let's suppose your g of t is only an exponential. Then n would be what would n be in that case?
Just e to the x.
Yeah, if I have like say e to the 4t as my entire g, then n would be 0. So then you would only have an unknown constant in this case. And if my example e to the 4t, if well, actually I'll just write that down. So let's suppose that g of t is e to the 4t. Then your particular solution is just going to be an unknown constant e to the 4t if 4 is not a root of your characteristic equation, and it's equal to constant t e to the 4t if 4 is one of the roots. Now, I've covered almost every possibility with this g. What possibility is left?
Force both the roots.
Yes. So if both roots are equal to 4, then what does my particular solution look like?
A not t squared.
Yes. Because that's why I defined s to be the number of times, a in this case is 4, is a root of your characteristic equation. So s can only be, for second order equations like we're dealing with, 0, 1, or 2. For complex cases, it can only be 0 or 1, because the complex roots have to be conjugates of each other. So that's your g, and that's your entire g. It's going to be one of these.
Is there gonna be situations when we have to do this method, or can we do the other way?
I'm never going to say you must use undetermined coefficients. You can always fall back on variation of parameters.
Okay, so it's not gonna be a situation where you can only do this.
Right. Not on the test. On the homework that's on this section, you have to. And I reserve a right to for a final.
In
Okay.
what?
I reserve a right to for a final, but not for this upcoming test. Is that? Oh, okay.
So
Well,
that GT thing goes down to the bottom,
um,
up there,
I'm not sure what you mean by that.
is that the bottom one, the one on the bottom?
Yeah. This is a one thing. Yeah. I think I'm out of time anyway, but we will continue with this on Monday.